right. So, who's got some ideas about what is representativeness? How can data be non-representative? You've had all coffee break to think about it. I'm sure that's all you were thinking about. Any ideas? Wait. Anyone else who's not a lecturer? Yeah, we've got an idea here. Sorry, with the, okay. We got Guillaume. Yes.
So for example, in photometric redshift estimation, you could, your whole data set probably say is between redshift 0 and 2, for example. But you could, for some reason, only select galaxies between below redshift 0.5, for example, so then they're not representative.
That's brilliant, yeah. So you're trying to estimate a quantity, and the data that you actually have, which is labeled, doesn't cover the full range of the thing you're trying to estimate of your true data set. Very good. What other ways could data be non-representative? Yeah, there was an idea at the back?
If for whatever reason, if you're trying to estimate the incidence of a disease, and then you have a majority of, like a huge majority of male samples and not female samples.
Good. Unbalanced training sets is what we'd call them. Yeah. Well, actually, that's an interesting one where, you know, because you can be unbalanced in the classes you're trying to classify. So you could be unbalanced in, or you could have different ratios in your training set and in your data set that you're trying to predict of a particular class. But that's an interesting one where your feature space might actually be different because you've maybe got majority male in your training set. So even though what you're trying to predict is a disease, but that may not fully cover your feature space because in your actual data set, there's equal number of men and women. Very good. Any other ideas?
When the features that you have don't quite map what you are trying to determine.
Yeah. And I mean, if you think about it in terms of, say, distributions, where the distribution of features that you have in your labeled set, so your training set, doesn't match the distribution in your true set. Yeah. Yeah, good. I think that just about covers it. So I've got, it's basically, essentially it's non-representative if the distributions differ between training and test set. When I say training set, I mean your labeled data that you know what it is. So you can have unbalanced classes and you can have feature distributions that don't match. So here's a way that you can visualize it. So this is taken from, again, the supernova classification problem that we're going to do. So these are not necessarily features, but these are aspects of the data. So like you've got magnitude here, probably in an R band, and you've got redshift. And these are SDSS supernovae. And you can see the spectroscopic set, which is in green. Oh, the labels didn't come out. The spectroscopic set is in green. Doesn't go as deep as all the supernovae that we know we have, and it doesn't go to the same redshift. So we lose the faint ones and we lose the far away ones. And that means that, well, this is a classic case of non-representativeness, and it causes problems in machine learning. So the question is, why is this a problem? Any ideas? At the wait, hang on a sec. Let's see if anybody else has any ideas, because you've just spoken. Anyone else? Not you either, wait. Anyone else? Someone who hasn't had a chance to talk a lot. Okay. Do you want to just wait for the microphone a bit?
Oh, if you want to classify something that is not in your training set, you perform something like an extrapolation, and this could go wrong in many ways, right?
Very good, yeah. It's effectively trying to extrapolate, which we know is always bad, right? Machine learning algorithm can only tell you about this region because that's the only region that it's seen. Anything that happens here could be complete rubbish. And so what will happen is you might do brilliantly in your training set, but then when you apply it to the real data, suddenly the performance of your algorithm tanks, and it's because it hasn't seen this region, and it's trying to extrapolate, and it usually does it badly. Good. Any ideas for what you could do to mitigate non-representativeness? Because it's essentially always going to be a problem in astronomy. Because usually it's easier to do things like spectroscopic follow-up or do further studies on things that are close and bright, right? So it's essentially always a problem in astronomy. So what kind of things could you do? Get kind of creative. What could you do to mitigate non-representativeness? Yeah, we got this idea here.
Well, in the case of an unbalanced sample, we could balance it in some way to give the same importance to the small group or class.
Yeah, very good. If you've got enough training data, you could just throw away the ones where there's too many examples, for instance. Good. Any other ideas? Yeah, you can do simulations. If you can. Sometimes you can't. Often you can't. I've just told you that these are problems where you don't have a good model for your data. So how are you going to simulate it, right? So we do that. That is very common, and it happens a lot, and I've done it myself. I've used simulations to create a fake representative training set. But the problem is you're only ever going to be as good as your simulations, right? So it's the standard problem with simulations. Yes?
A quick question. How did you, so you remove data? How do you do, so you
Right, so
exclude
if you-
data to get a representative data set,
Yeah,
but then
you
aren't you building your own representative, sort of building your own data so that, I mean, can you?
So how would you do it? Okay,
Yeah.
so I mean, say you had a sample of images of cats and dogs, but you have 5, well, okay, no, let's not use that. Say you have 2,000 images of dogs and you have 20,000 images of cats. You probably don't need that many images of cats, right? Because your training sample is big enough. And the problem is that these machine learning algorithms, even though we try, we give them metrics that are like AUC that's less sensitive to unbalanced classes, they will tend to learn better about the ones that they see a lot of. So what you can do is you can just say, well, I'll throw away a whole bunch of cats and still I've got equal number of classes so that it gets a better idea of the minority class. That is one way you can do it. It's actually very rarely the case you have so much training data you can do this, but it's an option. Corin? Wait, hang on, wait, maybe at the back. Yeah, you go. No, you go.
Okay.
Student first.
If you don't have enough representative, can we give them mock data so they can be equal and then see if the models satisfy us
Yeah.
in the way we want it to do?
Yeah, so you can exactly create simulations and you can see if your simulations are reasonable representations of your data set. It's a thing you can do. But at the end of the day, the answer is always going to be, it works well in simulations, it may or may not work on real data. Yeah.
That's why we have to evaluate the models we have at the end.
Yeah. Corin,
Can I say something slightly irritating and a little bit provocative?
I suppose I could just punch you in the face if it's too nice.
Okay. No, but seriously, I mean, you could argue at some level there is no such thing as non-representativeness, because whatever you do, you can always change that sample. So take the galaxy redshift, right? Go back 20 years, we don't know whether there are things, quasars higher than redshift 5 or whatever we got to, right? So you could claim that what you're doing at that time is unrepresentative, right? But depending on how you define your problem, what you know about the problem, that kind of defines the representation, right? So, if I could build an algorithm to do certain things, let's say classify cool stars, it's unrepresentative for the hot star. So what I'm saying is you define your problem to some degree through the data.
This will work in this region,
Right.
where your problem is defined, but isn't going to work outside that region.
Right. Whether that's wrong or not is sort of a question of the problem
Fair
you're trying to
enough.
address.
So I mean, what you could do in this case is just say, okay, I'll believe my predictions in this region, but I'm not going to believe them anywhere else. This defines my problem region, because this is the region where I know about supernovae, and I know very little outside of it. The problem is you very often want to do things outside of that region, right?
Sorry. By being representative, you're almost trying to, by the very fact that you don't have the data means that you don't know what's there.
Yeah, but
Right.
I mean, the problem is that we often have a few examples there. Like we know something about supernovae at high redshift. We also know sort of how things like their colors as such like evolve with redshift. So it's not like we know nothing, but we don't know enough to build a good training set. And that's where you need to use clever techniques to try and augment it.
Right, but of course, if the objects are really rare there, then if you overrepresent, but you'll probably get to that.
Yeah, exactly. You might be like, oh, well, we have 3 supernovae here, therefore we know something about this region, but you actually may be completely biased. Yeah. This is true. I mean, in general, whatever you do, it's not nearly as good as having a representative training set. You know, so you can be confident in the region that's defined by your training set. Outside of it. Okay, so any other ideas what you could do? There was one idea here.
I don't know if it's already been said, but instead of throwing data away, you do have a little data in the environment.
It's called data augmentation. Yeah. Could you use data augmentation? Now, in some cases, you might be able to simulate it. In the case with deep learning, we'll touch on it, you can do clever things like apply transforms to your data, right? You know, a picture of a cat and a picture of the same picture of the cat turned a bit this way. It's still a cat, but to the algorithm, it sees it as a completely new piece of training data. So you can do things like data augmentation, which is not the same as simulations. It's transformations of your data. But again, more or less what that's going to do is fill in these regions. If it's quite spotty, for instance, it's not going to help you extrapolate, right? You know, if it's never seen a poodle, it doesn't matter how many times I rotate a Rottweiler, it's not going to look like a poodle. So it's still going to be non-representative. Good, okay. So data augmentation we mentioned, there's this cool thing called transfer learning, which I don't know that much about, but it's basically, you know, if we know the different distributions, if we know what our training set distribution looks like in feature space, and we also know what our test set looks like in feature space, even though we don't know what the classes are. So for instance, we might know how things evolve with redshift, right? So we can see that they're evolving with redshift, but we might not know the classes. You can do this thing called transfer learning, where you kind of transfer your knowledge about one region to another. That can work in certain cases. The best thing you could possibly do is get more data, which is not always possible. What I think is the last question of this set, maybe, what is overfitting? Any ideas? Everyone knows what overfitting is on some intuitive level, I think. So if whatever your gut is telling you, give me that answer. Yes.
Yeah, when you have some kind of bias towards the result, no?
Bias, it can introduce bias, potentially. What else? Right at the right at the back.
So this happens when your model is so good with your training set that doesn't generalize very well.
Very good. That's a pretty good textbook definition. Do you have anything else to add, or is it the same? Basically the same. Right? Yeah. I mean, we all know about this. If you have 10 points in your data set and you fit it with an order 10 polynomial, it's going to fit perfectly. But it's not going to generalize, you know, if you fill in the gaps, if you put in new data, right? And so it's as simple as that. You, if your algorithm, if your model that's fit in your machine learning fits extremely well to the data because it's very complex And remember, these models are always very complex. They're highly nonlinear. There's often lots of parameters. That's why they work well. They're very flexible. But this means they're very prone to overfitting. And it might work perfectly on your data, your training data, but it's the same thing as fitting a very high-order polynomial. It doesn't generalize when you try running it on test data. Okay, so the last question is, how would you avoid overfitting in machine learning? It's a bit hard. Any ideas? If you'd read the questions beforehand, you probably would have Googled it and found out. Yeah.
Maybe you could try something like what you said before. Just do or take several samples or use different training sets.
Yeah, could you use different pieces of your training set? Yeah, exactly. Good. Antla?
And you can try to define some stopping routine, just like when we have these 10 data points, and we can start with, I don't know, with a 2 polynomial or 3 or something like that,
Right.
and just define, oh, when it's got, I don't know, something like that exactly, then stop.
Good. That actually leads exactly into this example. So this is a decision tree example where I limit the maximum depth of the tree, right? So how many decisions it can make. So this is my simple data set. It's a sine wave. So I'm doing a regression problem now, say, whatever. Now, in the case where the max depth is 3, you can see it sort of fits the data, but not particularly well. But it's not sensitive to all these weird points, these kind of outliers. When I make the max depth very deep, it's very sensitive to these outliers. But you can imagine that if I did this lots of times with different subsets of data, so I pulled out some of this data, sometimes these points will disappear because I've taken them out, right? And if I can average these in some way, you can have quite a deep tree that's still not overfitting, right? And this is why ensemble methods work really well. The way we usually talk about splitting up your data is training, validation, and test, right? So all of these subsets are labeled data, okay? You're not touching the data that you don't know anything about yet. You don't start there. You start with the ones that are labeled. So like I have my subset of supernovae that have had spectroscopic follow-up. Or I'm doing photometric redshift estimation. These are the galaxies that I know the redshift for, etc. I split up my labeled data into a training set and a test set. This helps me evaluate my algorithm. Because if I just evaluate it on the training set, it's usually going to do quite well, because it's seen everything in there before. So I need to test it on a subset of the data it's never seen before. And that tells you how well your model generalizes. The easiest way to test for overfitting is if you score extremely well on the training set and terribly on the test set, you are overfitting. Simple as that. If it's like a 5% difference, you're probably okay, because you will generally do better on your training set. The other aspect is this thing called a validation set, right? So this is particularly useful when you're trying to choose hyperparameters of your algorithm. What do I mean by hyperparameters? The k in k nearest neighbors, the choice of distance metric in k nearest neighbors, the number of trees in random forests, the depth of each tree, the number of neurons in a neural network, the choice of activation function. All of these things are hyperparameters that you have to choose in some way in order to train your algorithm, right? Now, you might choose a set of hyperparameters that does beautifully on your training set, but doesn't generalize to your test set. So you don't want to use your test data in optimizing hyperparameters. So you do a further division into this validation set. So now I can train on this small set, I can validate, and I can go, oh, that doesn't work very well. Let me try a different set of hyperparameters. Train, validate again. Oh, that's better. Let me try a different set. Okay, I think this is the best one. And then you try it on your test set. Why? Because you can again overfit. You can choose a set of hyperparameters that's so good for this training data but doesn't actually work that well in the validation. Okay. And scikit-learn, again, has a very easy way to do this. And in fact, we very rarely... questions.
One quick question, sorry.
Yes.
What is the... is there any best practice on what fraction of your data goes into the test set?
Yes, sort of. I'll discuss it in a second.
Okay.
Yeah. There was a question here?
Related to that, is it just a fraction of your data that goes into test set and training set? And do you have to worry about representativeness in the test set?
Yes. Yeah.
In the test set?
Definitely, yeah. So in general, you would randomly draw them. You would randomly draw a test set from your labeled data and keep it aside. So that if you do a random draw, it's probably going to be quite representative. But I mean, what I tend to do personally is once I've settled on an algorithm and a set of hyperparameters, et cetera, I will redo this whole thing a few times with different training and test sets just to check the robustness of my whatever performance I have against this. That is not always done. Often in machine learning literature, they'll just do it once, or they'll do it 10 times and take the best. And I'm like, well, that's not very representative. But anyway, so I would usually want to know like what's the average kind of performance. There was one more question, was there? Okay, so about fractions, it's weird that there isn't actually like a kind of hard and fast rule. There's kind of rules of thumb, depending on how much data you have. If you have very little data, you'll usually make your test set quite small, like 10% of your data, because you really need all that data for training. And then it's very important to do things like I just suggested, doing this whole procedure several times. But usually a split of like 70-30, very commonly used. You definitely want more in your training data, so the algorithm's got a fair chance of having seen most objects. But that's the sort of default, maybe, will be about 70-30. So this is very rarely done yourself. You very rarely choose this validation set yourself. Because once again, you run into the problem that I might have chosen a validation set that's particularly hard or particularly easy, just by a pure random chance, especially if you only have, like, say, a few hundred examples. So what's actually done when optimizing your hyperparameters to try and avoid overfitting is this thing called cross-validation. So in this image, in your mind, replace the word test with validation. I don't like that they use the word test here, because this is not what you would do. Your test set should still be separate at this point. This is your validation set. So instead of doing this once, just picking a validation set and a training set once, you can do it lots of times. And so very common is 5 or 10-fold cross-validation. You'll do it 5 or 10 times, where you randomly choose different subsets of training and test, and you run your algorithm, right? And this is particularly helpful when choosing hyperparameters, because you will choose a hyperparameter and then do all of these and average the performance between them. So your choice of hyperparameter might be great for one random realization, but rubbish for the rest, right? So this just helps you be robust to randomly getting a training of a validation set that's particularly good or bad. And this is a function that you can use in scikit-learn. There are many. There's also, I mean, we tend to use grid search CV a lot, but we have much better optimization algorithms, so I'm not really sure why we actually do this. Anyway, if you've only got a couple of hyperparameters, it's pretty fast. So you'll define a hyperparameter grid, like the number of, again, like the number of neurons in a network can be 3 to 10, or the number of decision trees will be 100 to 300, things like that. And then this will automatically train, simultaneously train and optimize the hyperparameters for you. Are there any questions before I move on to the very last part of the talk? Yes.
So I have an example in my head, which I'm not sure if it counts as overfitting. So I just describe it. So for example, in image classification, say you have two categories that you care about, cats versus dogs. Okay. But somehow your data, your images of cats, they always say next to a flower pot or something like that.
Right.
And therefore, when you do see a dog that's sitting next to a flower pot, but you classify as a cat.
Yeah. So
does that count as overfitting?
It's not quite overfitting. Well, it sort of is. It's more like a kind of non-representativeness, I think. Machine learning algorithms are incredibly sensitive to this. Incredibly. There are so many cases where an algorithm did brilliantly well, not because of the actual data, but because there was some little piece of metadata. Like, I don't know, in the one class, they, well, a great example was, I think it was the US military, was using deep learning for identifying tanks. Is there a tank in this picture or not? And it had 100% accuracy until they realized that all the pictures that they'd taken of tanks were taken on a cloudy day, and all the pictures where there are no tanks was taken on a sunny day. So in my mind, it's not quite overfitting so much as non-representativeness. You've got a training data that only has this small part of feature space and isn't actually exploring all of the feature space. And again, these algorithms are very, very sensitive to it. You need to be very careful if these things happen. There's a question there. Last question. I think we should move on to get onto the tutorial.
I think it's short. So the algorithm selects by itself the number of hyperparameters, doesn't it?
No, you choose.
We choose, okay, but which would be the coherent number of hyperparameters to start?
It depends completely on the algorithm. They all have default values, so you can, like in scikit-learn, you can just run it and see what happens. But you need to have some understanding of the algorithm and the effect that the different hyperparameters have before you should decide if you're going to leave it to default or if you're going to change it. And there's some documentation in scikit-learn about which parameters are really important. You know, a lot of the time they're in there, you could tweak them, but they won't make a difference. But there are some that will make a big difference. And so you actually need to know a bit about each algorithm before you know which parameters to vary. You can just use them out the box. They will work for most problems. But if you want to get it better, you need to be looking at optimizing hyperparameters.
But you can use also the grid search cross-validation with all this grid of parameters.
Yes, of course. And I mean, the only problem here is computational, right? If you have 10 hyperparameters, you're in a 10 by 10 grid. You know, and you have to retrain and validate 5 times, say, for every set of hyperparameters you look at. So this quickly becomes boring, basically. But if you have a large amount of time, in general, you do want to optimize your hyperparameters at least. Okay, I'm going to move on to a few examples. There are many, many more examples in the literature than what I'm going to talk about, but here's a couple of cool ones. I really like this paper by a friend of mine on finding the weirdest SDSS galaxies in spectra. So they had quite a large data set. I think at least 100,000, maybe 1 million spectra that they looked at. And they actually used the individual fluxes as a function of wavelength as their features, which was quite a large feature space. And they used random forests in a kind of novel way to assign a weirdness score to each galaxy, which was pretty cool. And then what they did was they took the weirdest ones, which are these ones here, and then they had a look at trying to figure out what made them weird. And they learned some interesting astrophysics. They found some new objects that nobody had really seen before, and did some interesting astrophysics with what's going on with these galaxies to make them so unusual and so different from the others. And I particularly like this example because a lot of people want to throw machine learning at problems that's not necessarily appropriate, or throw machine learning in critical pipelines where we need to understand the uncertainties, we need to understand the probabilities, we need to understand all the statistics, and it's harder with machine learning than it is with Bayesian statistics. But this is a great example of data exploration with machine learning, where it's not critical to some kind of cosmological pipeline that this number means something and is interpretable. It's instead a way of exploring your data set using machine learning, which I think is a very powerful application. Corin.
So this was presumably a supervised learning algorithm. So is this also the distribution of the training set? So, and if so, how did they assign the weirdness in the first place? Or are these high numbers actually an extrapolation of the...
Yeah, no, it's not an extrapolation. I don't want to go into the details now. It's a very, we can chat about it later. It's a very interesting way of using random forests that involved creating synthetic data that didn't have flux correlations, and they had real data that did have flux correlations, so that you were, and then trying to distinguish between real and fake. And then there was a particular criterion on galaxies that were weird. It would turn, depending on where they ended up in the random forest. Yeah. So that's the 10-second version. Another example that I really like is, and there's actually I'm not sure if it's out yet, but there's an updated paper where this is done with real data. So this is with simulations, where they use deep learning to find gravitational waves in the LIGO signal. And they did this by training it on simulations, on loads of simulations, a huge amount of data. But they found what they could do is they could not only find the gravitational wave more effectively than a matched filter, right? It was also significantly faster than a matched filter. It was like 100 times faster. It was ridiculous. But you could also predict the masses of the black holes and the parameters in the model, which was quite interesting. That's where I'm a bit like, okay, now we need statistics in those, with those parameters, so that might not necessarily be the best way to get those. But for finding these objects, it was a very effective algorithm. And the last example I want to talk about is what we're going to do today in the tutorial. So this is supernovae. You probably all know that there's basically two types of supernovae. There's the type cosmologists care about, and then there's the rest. So the type we care about is the type 1a supernovae, which probably looks something like this, maybe, where you've got a white dwarf accreting matter off a companion, or you've got two white dwarfs merging. Jury's still out. And the idea is that when they hit a specific mass, the Chandrasekhar limit, they explode. And because they explode at the same mass, they explode with the same brightness. So we can use them as standard candles in the universe. That's the theory. Empirically, they work extremely well. Theoretically, we don't actually understand them. But you get great, so this is the Hubble diagrams, this is redshift, this is the distance modulus. And so we are sensitive to the expansion history of the universe, and we're actually extremely sensitive. I mean, these are incredibly precise measurements with supernovae. But those are only the type 1As. The non-1As are quite bad. Core collapse supernovae can happen at any mass. So if you try to use them as standard candles and put them on this diagram, they tend to be fainter than 1As, but they'll be all over the place, right? There'll be lots of scatter. They don't lie on this very nice line. So we've only really been interested in type 1As. The problem is, I don't have a slide on it, but the problem is for a survey like LSST, or even current surveys like DES, there are thousands of supernovae. LSST will find at least 100,000 supernovae over its 10 years, probably more, and not enough resources to spectroscopically follow them up. So we won't know the type. So this is a great machine learning problem, because what we do have is photometry. We have in different filters, so these are, DES filters, you do have the light curve, the brightness as a function of time, in different colors, basically. And there are subtle differences between light curves. This is a very exaggerated example, but there's subtle differences between light curves between different types. And crucially, there's the correlations between the colors change for different types. Humans can't do this. Even experts can't look at a light curve and say for sure if it's a 1A or not. But computers can. Machine learning can. So what I'm going to do, so this is the problem, that we have photometry, but not spectroscopy for all our supernovae. We'll have spectroscopy for a small subset, maybe 5 or 10%. All right? So using that training set, can we train a machine learning algorithm to predict the class of the unknown supernovae? So I'm going to take you through this as an example of the full procedure of machine learning, from data to feature extraction, to choice of machine learning algorithm, to your final classification and your performance metric. And then you're going to do it. So in the tutorial, I've done the feature extraction for you because there's some domain knowledge there, and I'm going to explain it in a minute. But the machine learning bit is up to you. And you can do it completely differently to how I've done it. It doesn't matter, play. But by the end of today, you're going to have a full worked example, end-to-end, how you would do machine learning classification problem. And hopefully you could apply it in your research. So we start with the features. Now, one of the biggest issues with the light curves is that we can start detecting them at any point on the light curve. It's random. Wherever the telescope happens to be pointing, there might be a supernova that went off a week ago. There might be a supernova that's just gone off. So we can't be sensitive to the position of this peak, right? That's one of the key things. So that's why if you just give a machine learning algorithm raw data, they do very badly. They aren't really able to classify very well. So we tried 3 different feature extraction techniques, and this is also something I'd recommend doing. Don't just settle on a set of features because they seem sensible. Try different ones. Be a little creative. Use domain knowledge. Use standardized techniques for dimensionality reduction, things like that. Try different features and test how your algorithms respond to them. So we used one, which was template fitting. So supernovae are a great example where we don't have good models for light curves. It's very difficult to predict, well, at the moment it's impossible to predict a light curve of a supernova given some parameters. But we have empirical models based on past data. So we have models with like 5 parameters for predicting these light curves that we can fit that are based on known type 1a supernovae. And you can use those parameters as your features. And because it's a fit, we're not sensitive to the position of the peak, because that's one of the parameters that we fit for. You could be a bit more general and say, well, we don't want to assume so much knowledge about type 1As, but we know that supernovae all kind of have the similar shape. They go up, they have a flat bit, they come down. And so you can do general parametric fits to the light curves and use those parameters as features. And we tried 2 different parametric fits. Or you could be really agnostic, and you could say, let's assume we know nothing about supernovae, we just know that they're signals in time. And there's this great tool called wavelets, where you can do a wavelet decomposition of the light curve. It's a bit like a Fourier decomposition, but your coefficients are sensitive to frequency and actual location in the time domain. And the kind of wavelets that we used are not very sensitive to translation, right? So that deals with this problem of not knowing where the peak is. So you can see I've come up with 3 very different feature extraction methods for the same data set. Right? I didn't just start with one and go with it. And I just wanted to say that the interesting thing is that I don't say model independence, it's sort of knowledge independence. This requires a lot of knowledge about type 1As. This requires very little. And you might want to try doing things like that in your own research as well. How could I be more agnostic about my data? So this is what our pipeline ended up looking like. We start with data. We have 3 different feature extraction methods. Well, there's 2 in here, so we actually have 4. Because I was sort of starting out with machine learning, we tried out 5 different algorithms. More, actually. Also, there's random forests here. And ran each algorithm on each set of features and produced rock curves for each to have a look. And we get your classified supernovae at the end. Sorry, this is not actually public unless you're in LSST yet. But if you are in LSST, you can have a look. Okay, so this is just about the last slide. Yeah?
Going back to the rock curves, even not valid, but how do you like them? Which one would you say is a bad classifier? Which one would you say is a good classifier of your particular?
Yeah, good question. So if you actually, it's a bit small here, but if you actually look at it, this one, which is boosted decision trees, which is a kind of ensemble method, at every point on this rock curve, the purple line is above all the other lines. So here it's unambiguous. This is the best algorithm. No matter what point you are in the rock curve space, BDTs were the best. In some of the other cases, some of the other algorithms actually crossed over, and then we have the situation we were discussing earlier about which region do you care about. But actually, in every case we looked at, this was the best algorithm.
Can you repeat the name?
Boosted decision trees. It's very similar to random forests. It's just a slightly different way of averaging the decision trees. Random forests gave statistically the same performance, basically. This was just slightly faster. So this is actually a summary of all of the results. So when you do this yourself, you can actually compare what kind of AUCs you get. This is a very complicated plot. On the y-axis, I've got AUC, so remember 1 is the best. 1 represents perfect classification. I've arranged on the x-axis the algorithms kind of according to awesomeness, generally. This is naive Bayes, which has a lot of assumptions, and they are always broken, so it doesn't actually work very well. K-nearest neighbors, artificial neural networks, which we did this morning, support vector machines, another very nice algorithm, and boosted decision trees. What I've got here in different colors is my different feature extraction methods. So now not only can I test how good are my algorithms, but how good are my features? Are these good features for describing this data? And so what you see is several things. First, you'll notice boosted decision trees is the best. Generally outperforms the other algorithms. But not by a lot. These ones are relatively close. The second thing you notice, SALT2 and the wavelets, those sets of features, outperform, except for these crappy algorithms, they outperform the parametric fits. So we're saying either you want to use lots of knowledge that you have about supernovae, or you want to be pretty model independent. Doing this kind of in-between thing doesn't actually work very well. And that was very important because some people have built classifiers based on those parametric models, and we were saying there are better features. And the nice thing about the wavelets is that it's independent of all the assumptions that go into SALT2. Right? So this is very data-driven. The last thing I want to point out is that we looked at representative and non-representative data. Right? The representative was randomly drawn from the labeled data, and the non-representative was non-representative in that plot that I showed you. So it didn't go to the same magnitude, it didn't go to the same redshift. And so you can see in all cases, the representative one does a lot better than the non-representative, which is exactly what we said. It struggles to extrapolate. And so now the next project we've been working on is how to deal with the non-representativeness problem. Okay, does anyone have any questions on this problem? Because this is what you're going to be working on in the tutorial.
Can you specify or give an idea about...
Yeah, sorry.
Can you just give an idea of a hyperparameter you're using each algorithm?
Oof, I can't remember. You'll have to look in the paper. I mean, these are naive Bayes has no hyperparameters. K-nearest neighbors, I think it settled on 7 neighbors. Artificial neural networks was like...
I don't mean the options. The hyperparameter is wrong. I mean, the number of parameters in the model.
Well, you've got to be careful about parameter versus hyperparameter, right? Because in theory, in a neural network, every weight is a parameter. And your hyperparameters are the things telling you how many weights, et cetera, et cetera. So parameters not actually that well, probably not the right question here, right? So, yeah, I'm not too sure how I could even answer you there. Are you asking like how complex are the models, kind of? Yeah, I mean, obviously these ones are more complex than these ones, right? And it shows in the performance. There's a lot of things that can be, less things that can be tweaked here than here. But I haven't done any formal measures of complexity in those algorithms, yeah. Question?
In your light curves, I was thinking the important things not only where is the peak, but also the measurements don't have to be in the same interval, or you just interpolate between
that's a good
the
point.
points.
So you don't have to interpolate for these 2 feature extraction methods because they're fitting models, right? This one you do. To get the wavelets out, we had to do some interpolation, so I actually use Gaussian processes to interpolate there and interpolate on a regular grid. Yeah. Any more? Yeah, there's a question at the back.
So if you go back to the slide with the results, where you compare different algorithms, so the y-axis indicates you from the area under the rock curve how well a specific algorithm performs, right?
Yep.
And then you test, it's indicated by different colors, different models, on how well the specific algorithm does.
Yep.
Right? Can you please repeat again what was the difference between the model one, so the models, and SALT 2? So
Yeah.
SALT 2 must also incorporate some prescription, right?
So these are the different feature extraction methods, I would say. I would be nervous to call them models. The only reason why the word model comes in here is because it's a parametric model that we fit to the data, and we use those parameters as features. So these 4 things are these things, right? So this is SALT 2, the templates. Model 1 and Model 2 are parameterizations of the light curves, and wavelets is wavelets, right? So they are your feature extraction methods. I mean, this isn't a model. It isn't what I would call a model. It's a decomposition method. Yeah. Yeah.
If I understood correctly, you are using spectrum to get this template fitting. Then you are using the photometry. So you are just both using spectroscopy and photometry. But when the sensitivity will be different from one part the other part. So how do you deal with that?
Yeah, so this template fitting method is standardized within supernovae, and it's based on a series of spectrophotometry measurements, right? So, and it's mostly based on SDSS data. In this particular example, it's actually a cheat. So this actually I expect to do better than I would on real data, because this is actually tested on simulations. So we first had to show that it works on simulations, then now we're doing it on real data. But the simulations are made using the same templates. So we fully expected this to do very well. So there they will match perfectly. Now, in the case of real data, it is actually an ongoing problem in supernova cosmology. We kind of know that this is crap. It's not really that good. So people are working on improving this model, and the calibration between the data that you use to construct the templates and what we're looking at now may be very different. Yeah. Well, not very different, but it could be different. Yes.
And do you have an idea why model 1 and 2 performs so bad? Is it just the reason that you said that you tested this on simulated data, so that's why the template fit in?
No, I wouldn't expect them to do very well on real data either. I'm not surprised the templates did well on the simulated data for that reason, but also they will do well in general because the parameters that come into the templates are things like color and stretch, which are very well behaved for 1As, and they have a very broad distribution for non-1As because it's a bad model. It just doesn't fit that well. So it's a reasonable thing to do. Whereas in this case, there's enough flexibility in these parameterizations that they can kind of fit anything that looks like a supernova, and there's not really any physical reason why the parameters should be that different between the different types. And the wavelets are great because they're incredibly sensitive to what we want, which is the actual shapes of the light curves and the correlations between the different colors. So that would be my interpretation of why they work well. And that's a good question. That's a good sort of teaching moment, that interpreting your results is really important. Understanding why do these features do well versus why don't they. And this is where things like random forest doing the feature importances can help, and being able to explain these physically motivated features helps. Okay, I'm going to move on because we need to get to this tutorial. But before we do, we can have some fun, because we all like doing discussions. And I would like you to get into groups and have a discussion for about maybe 5 or 10 minutes. So what I recommend is that each table like this table, turn around and face that table. The next table, turn around and face the table behind you, etc. So that you can just get into kind of these little mini groups and discuss this very important question. What is the difference? Okay, well, actually, maybe we should do the discussion on the next question. So let me maybe first ask the floor. What is the difference between machine learning and statistics? Who's got an idea? I'll let you discuss the next one, I think. Wait, hang on. Wait. I'm sure you guys know. Students. Yeah, you've got an idea. Say it out loud.
Well, I think that machine learning is unsupervised. Instead, statistics need supervising.
You can do unsupervised machine learning, but there is supervised machine learning, right? You might have a case where you know the labels of your data. Should you use statistics or machine learning, right? So what's the difference between them? So we're getting there. There was an answer there.
Well, the machine learning produces the models, right? And for statistics, we're using models.
So statistics, we need to know the model before we can get started. Good. Okay. What else? Is that what you're saying? You had the same idea? Any other ideas? Okay, fine. Brendan.
You can say yours. I don't know what. Yeah, I was just going to say that joke about how data science is statistics on a Mac. So.
Or you
no, 0 points for that answer.
Machine learning is statistics without the rigor.
Yeah.
I don't know who said that.
So this, in some sense, this division between machine learning and statistics is done. You know, there's been these kind of two different communities that have developed. There's mostly computer science, the machine learning side, and there's the statistical side. And a lot of the principles are the same. And it really is a case of, and you know, we saw as we went along, you still have a model, you just have a very general prescription for coming up with this model. Your model still has parameters, but in machine learning, we always optimize those parameters instead of marginalizing over them, right? So on some level, there isn't actually a difference between machine learning and statistics. And these fields are meeting. They are getting closer and closer together. But there are cases where, like I said, you may not have any physically motivated model that you can use, because if you have that, I would say you should always use statistics. If you've got a good model, use Bayesian statistics. You know, if you're doing classification, you're doing model selection. If you're doing regression, you're doing Bayesian inference, right? As long as you have a model, use Bayes. I mean, we've seen how powerful Bayes is. But there are cases where we don't have a good model, and there have been problems that have been completely unsolved for years for this reason. And so that's where machine learning is really powerful. So the thing I do actually want you to discuss is this question here. And we'll do about 5 minutes. So get into groups and discuss this question. I'm going to ask each group to kind of give an answer to this. You need to decide, should you use machine learning? And by machine learning, I mean the kind of thing that I've described today. So where you're optimizing, so you don't know about uncertainties, et cetera, you're doing model building. Or should you use statistics like you've learned over the last 3 days for each of these problems? And so if you can arrange yourselves, so if you can turn around and talk to the people behind you and discuss. All right, let's get back together. Okay, stop discussions. I know how much we love discussions. So I hope you had some really good arguments, because I picked some quite contentious examples. So who wants to go first? Who wants to answer the question of what would you use for predicting the weather? I mean, I can just randomly pick out groups. Yeah, okay, let's start with this. Hang on. I think let's go group by group. So let's maybe start with this group here. So this big table over there. Yeah, anyone can answer. What did you decide?
I don't think there was consensus.
So just for the first one, for predicting the weather.
Predicting the weather, I think there are pretty good models that use previous data to then infer the new one. So I would say statistics. Yeah.
Right, cool. Statistics was the vote there. Anyone have a strong argument against that? Yeah, so preferably in the same group, yeah?
We were not in the same group.
Oh, sorry.
No. But
okay,
what
fine.
no, like, it depends on, do we want to have a good prediction for tomorrow or for this week, or we want to do like the next year, or like, do you define climate changing as a prediction of the weather? If yes, that's something like that you can have a lot of data from different years. You can have a really good representatives, and the machine learning is going to work fine here.
Yeah.
So it depends on what the weather prediction should be.
Yeah, good. So I mean, my personal feeling on that is I don't actually think we're all that good at predicting the weather. Quite often we'll say, oh, it's going to pour with rain and then it's sunny, or vice versa. And so when I read up on this, commonly what people do is statistics, very, very complicated statistical modeling. And I couldn't find too many examples of machine learning, but it feels like a really good machine learning problem. So and maybe there's scope there if anyone wants to jump into meteorology. Last comment on this, and then we're going to move on from predicting weather.
It's a question. Can we use machine learning? Could we use a machine learning algorithm to predict the weather and predict a weather that we have never seen before?
Can we use it to predict the weather that we've never seen before? I definitely don't think so. Well, I mean, you could, but it will probably just come up with rubbish, right?
So in that case, does that mean that we cannot use machine learning to predict the
Well,
weather?
I mean, basically you can say, what is the probability of these particular weather conditions tomorrow, given all of this data that we have before, right? It's not quite extrapolation because you're trying to estimate things from the same distribution. We know it's not going to suddenly be completely different. Okay, can we move on? Maybe, yeah, because I'm just conscious of time. So maybe in the next group, okay, you really wanted to talk. It's your turn to talk. What about removing foregrounds? What does your group think?
I don't know, because
Good answer.
our group, I don't think we had an agreement. Do we? No. So for me, I think removing foregrounds is for statistics. I'm doing some 21 centimeter stuff, and we have pretty much clear, artifacts or foreground stuff. So I can just model them easily. And as you said before, just going this, if I can model something clearly, then I can use statistics, Bayesian or whatever.
I agree with that. And this is what is done. And I think the most important thing is it's very critical that you understand your uncertainties in this process, because you're trying to get out precision cosmology out of these maps. So it's really important that you understand the effects of your modeling, and that is just much easier in statistics than with machine learning. So I would say that's probably a statistics problem. Okay, let's maybe have the group at the back on this side. What did you think about testing for rare diseases? Say at the very back.
Very back.
Okay, fine.
Well, for testing for rare diseases, it's already being used in diabetes and I think HIV as well, and lung cancer.
What's its?
Machine
Statistics or
learning.
machine learning?
Machine learning, yeah, definitely. Well, statistics has always been used in biostatistics, as far as I know, and they are moving more towards machine learning right now, especially with rare diseases and long term. I don't know what the name is.
Yeah.
Diseases. So, yeah, machine learning is applicable there.
Yeah. Do you guys have any comments on that, given your backgrounds, maybe?
May I add just one point about the weather? It is already being applied. Machine learning is already being applied.
But it's quite new, right? Like
no. You have a model, and you have actually something called data assimilation, which you feed input data into your model. And so the model is already being updated as new data comes in. And if you go to the ECMWF website, they already have ROC curves about that. So
Fantastic, good. I'll look it up. Do you want to talk about the rare diseases?
Yeah, about the rare diseases. I guess the thing I would add is that it's sort of probably both, in the sense that there's a lot of work, say, for example, in the UK, there was some publicity about the NHS turning over patient data to the Google DeepMind project to do, to build machine learning models to identify particular conditions. So as far as, there's definitely a demand for machine learning to take very complicated, high-dimensional data sets and use them to predict disease status. But then, like in the sort of the examples that Brendan and I talked about, where you have, so the disease is rare, and then you have a sort of a positive probability assigned by a chemical test or by a machine learning algorithm to the disease state, then you definitely need to apply a Bayesian analysis in order to guide your decision on how to use that, that predictive output.
Yeah, that's very good, yeah. And I maybe we'll just add that one of the issues with machine learning is the interpretability issue, where an algorithm may make a decision that could affect a human's life, right? Somebody could die if this algorithm is wrong. And so there is issues around if you can't understand why the algorithm made that choice, there's obviously a ethical and political issue there. So that is the one maybe danger around machine learning in that area.
Yeah, if I can just add a comment specific on the rare diseases, but it's perhaps more general. I think where you have strong domain knowledge about the situation, it can be very difficult to get a machine learning algorithm to capture it in the way that you want.
Yeah.
So if you really understand, I think this is also why I say, as you said, for removing foregrounds, I don't know, but I can imagine there, you don't want to use machine learning because you have a very good understanding of the situation. You can forward model very well.
There's no reason to, yeah.
And also I think related to the rare diseases, I mean, you and Maura said this, but if the tests themselves are not very strong, say for example in breast cancer testing, you're much more dependent on the prior. Or the background rates.
And incorporating prior information into machine learning is
very hard.
non-trivial. Okay, let's move on to what about removing artifacts, things like CCD errors, aeroplanes, and let's do this sort of group in the middle-ish. Someone from that region answer. Okay, let's do these.
Just give the mic to somebody.
Yeah.
Put them on the spot.
Yeah. Yeah, one table before. Yes. Okay.
To removing artifacts, we think that we can use machine learning because sometimes, for example, with aeroplanes, it's very difficult to model these things. So, yes.
Yep. Yeah, I think it's actually an interesting one. It depends on what you want to do. If you just want to throw away any image that's got rubbish in it, machine learning is great for this. And in fact, this was a major problem in the dark energy survey. They had poor students and postdocs and everyone in DES having to hand flag images every day, a whole bunch of images, like, is there an artifact or is it fine, whatever. And now it's just done with machine learning and it's much, much better. But maybe you want to do something more subtle, like trying to actually still use the image, but maybe remove cosmic rays from in there, and then it's a bit more like the foregrounds problem. And I don't know how much people do, but you could potentially use statistics for that, because we do know something about these artifacts. Okay, so let's move on to the last one, photometric redshift estimation. Does this table here have opinions about it? Yeah, machine learning?
Machine learning, yeah.
No reason why?
I would say that if you use traditional filter bands, I would use statistics. But now with surveys as J+, that you have narrow bands and you have lots of them. So maybe now that you have a higher dimensionality photometric space, maybe it would be good to use machine learning.
So this is very contentious, I'll say. Okay. All right, yeah, you have a last comment on this, and then we'll move on.
I disagree with that opinion because my reason is photometric redshifts has generally very large error bars, and as far as I understood from this workshop, the Bayesian or statistics are very good, to construct your errors or to understand your errors. So I know some photometric redshift errors like 2 or 3. Come
Yeah,
on,
yeah.
You say 5 plus or minus 3 redshift, so it's huge.
So this is very contentious.
That's why I'm saying it's
Yeah,
statistics.
there are machine learning algorithms for photometric redshift estimation. There are statistical algorithms for photometric redshift estimation. It's not clear which one performs the best, but there's a lot of arguments, I personally think, for using a statistical model, even if you don't have a really great model. I mean, these error bars are very big, but it's much easier to incorporate the effects of those uncertainties later down the pipeline if you do a statistical approach. And there have been some very interesting approaches that people have come up with using the data in interesting ways, where you don't just estimate the photometric redshift of an individual galaxy, but you estimate for a population, and you actually have a hierarchical model for getting your final cosmology out. But there's a lot of people in the machine learning camp in the photometric redshift estimation. So I would say that the jury's out on that one. Okay, so the last 2 slides these are some important concepts that some of which we haven't talked about very much, like feature rescaling. Some algorithms require you to rescale your features to be centered on 0 and with roughly a unit variance. So random forest does not. Neural networks do, for instance, require rescaling. We talked a bit about overfitting, always be sensitive to it, hyperparameters, cross-validation. Dimensionality reduction is key. There's a lot of great dimensionality reduction techniques that you might use if you have a high-dimensional feature space. Care about representativeness, care about your performance metrics. And if you go onto Scikit, or if you just Google scikit-learn algorithm cheat sheet, this is great because it asks you a series of questions to help you decide what kind of algorithm you could use. I like the first one. If you got less than 50 samples, don't even bother. I would put that number quite a bit higher, actually. But you can have a look if you're doing regression or clustering, if you want to do classification. So, huh?
Yeah, good.
Sure. So you can just have a look at that. Okay, so what we're going to do now is the tutorial, which hopefully everybody has gotten working. So the tutorial is on supernova classification with machine learning. There's a lot of stuff that you can read, some links. I've done the feature extraction for you. I've given you a set of SALT2 features that you can use to do machine learning. I stopped there. So I haven't done a bunch of stuff that you can just run and see what it looks like. You have to do some real work now. And the reason I've done this is I want you to play around with making different choices than what I would make, and see what effect it has on your results. So everything you need is there. Everything you need is on the scikit-learn webpage as well. And I'll go around to help you. And there are steps, like what steps do you need to take? But from the materials and the lectures and from stuff that you can use online, you should be able to, by the end of today, have a working machine learning example. Okay. So that's the end of my slides. There's some references. I'm not a big textbooks person. I don't know, maybe it's just me, but I learn much better with sort of just-in-time learning, getting bunches of stuff off the internet. So most of my links are online courses or tutorials and things. But there's a very good book by Bishop, and there are lots of other books that you can look at.